forward bias PN junction. If V volts is applied across the PN junction with the P side connected to with the positive side connected to the P side and negative side connected to the N side, under forward bias condition, the voltage across the PN junction decreases as the potential gradient across the junction is in opposite direction to the applied field. The diode current I0 is I is equals to e to the power QV/KT minus 1. I0 is QA dP upon LP Tn plus Dn over Ln into Np. For low-level injection, minority carrier injections are considered. Under forward bias condition, excess charge carrier photon electrons in P type and excess charge carrier holes in N region. Distribution of excess charge carrier in P region and N region is the current due to the excess hole across Xn region is IPXn is equals to minus QA dP differentiation of the whole distribution function will give me this value QA dP 1 over LP del PXn, which is QA dP over LP Pn e to the power QV/KT, where V is the forward bias voltage minus 1 e to the power minus Xn/Np. This will give me the current across of hole due to Xn. At Xn equals to 0, IP0 is QA dP over LP Pn e to the power QV/KT minus 1. Now here you can look at this diagram. I want to tell you that if this is an dopant where P region is heavily doped in comparison to the N region, thus the depletion layer is extended more in P region. Oh, I'm sorry. It must be the opposite, that P region is lightly doped and N region is heavily doped. So the depletion region is less in N region as compared to P region. And where the electrons and holes cross each other, they're the majority carrier in the region, but when they come to the edge, they becomes minority carrier. And with an exponential decrease, they decrease for a diffusion length having a constant time period. Okay, with Pn plus del Pn. Del Pn is a minimum value to which they decrease. Similarly, if we calculate for Xpn equals to 0, that is at the edge the concentration of electrons, or firstly the current, that is minus QADN over Ln Np e to the power QV/KT minus 1. Now the total diode current will be, if we add both the value, that will combine to give us QADP/LP Pn plus DNLN into Np e to the power QV/KT minus 1. I0 is this equation. If we put diffusion constant coefficient with the diffusion length, then the formula will be equals to diffusion length divided by the time period, and will give me this value of I0. If we